Welcome to the online training, Module 4, Lesson number 2. Lesson number 2 will focus on multiple regression analysis. In this lesson, we'll look at the introduction to multiple regression analysis, and specifically, we'll look at the 3-variable regression model, especially on notations and assumptions. Then we'll move on to interpretation of the multiple regression equation. And lastly, we'll look at the ordinary least square estimation of the partial regression coefficients. As a matter of introduction, we may recall that in the consumption income example that we talked about earlier, it is assumed implicitly that only income is related to consumption. So we can learn a regression model as we saw in lesson 1, simple regression model, by looking at consumption expenditure as depending on income. However, economic theory is rarely so simple. There are many other variables that are also likely to affect consumption expenditure. Therefore, the 2-variable regression model should be extended to cover more than 2 variables, which gives us multiple regression models. In other words, multiple regression model, these are models where the dependent variable y depends on more than one independent or explanatory variables. Now, the 3-variable regression model, the 3-variable population regression function may be written as yi is equal to beta 1 plus beta 2 x2i plus beta 3 x3i plus the error term ui, where y is the dependent variable, x1 and x2 are the explanatory or independent variables, and u is the stochastic disturbance term, and I is the ith observation, because there would be several observations under each variable. In case the data are a time series, the superscript t will denote the tth observation or observation at time t. So if you look at equation 4.2.1, the population regression function, beta 1 is the intercept term. In other words, its mechanical interpretation is that it is the average value of y when x2 and x3 take up the value of 0, or they are set equal to 0. The coefficients beta 2 and beta 3 are called the partial regression coefficients. Now let's look at the assumptions. Here we extend the assumptions that we looked at under the simple linear regression. There were 7 assumptions, if you recall. To those 7 assumptions we talked about in lesson 1, here we add 2 more assumptions. Number 8. So we are considering all the assumptions under simple linear regression function or model are also applying to the multiple regression analysis. So in addition to those, we have number 8, which is no exact collinearity or multicollinearity between the variables. In other words, there is no exact linear relationship between x1 and x2. There is no correlation between the variables included in the multiple regression model. Assumption number 9 is that there is no specification bias. The model is correctly specified. You may remember, we also talked about this, that the value of the error term is 0 in the previous, one of the previous assumptions that we looked at, which is related to this, that there is no specification bias. In other words, the model is specified correctly such that the error term is 0. So the logic behind the problem of multicollinearity is that, for example, suppose in equation 4.1.2 that we saw, the population regression function, y, which is the dependent variable, and the explanatory variables x2 and x3 represent consumption expenditure, that is for y, income, that is x2, and worth of the consumer, x3, respectively. In postulating that consumption expenditure is linearly related to income and worth, economic theory presumes that worth and income may have some independent influence on consumption. So in other words, there is no collinearity between income and worth such that we can determine the effect or influence of worth on consumption expenditure. We can also determine the influence of income on consumption expenditure independently. If not, in other words, if these two, income and worth, are not independent, then there is no sense in including both income and worth variables in the model because they are influencing each other. So in essence, it means they represent one model. Rather one variable. In the extreme, if there is an exact relationship between income and worth, it means we have only one independent variable, not two. And there is no way to assess the separate influence of income and worth on consumption. Why? Because if income and worth influence each other, it means while we are determining the influence of income on consumption, at the same time, we are also determining, or we have some influence from worth that is coming to income. Similarly, when we are determining the influence of worth on consumption expenditure, at the same time, we have some influence from income that is coming into the worth. In other words, the assumption of no multicollinearity requires that in the population regression function, we include only those variables that are not exact linear functions of one or more variables in the model. So in other words, we include only those variables that do not influence each other, such that it will be possible to determine the influence of each of those explanatory variables on the dependent variable. Let's look at some points to note on multicollinearity. The assumption of no multicollinearity pertains to our theoretical population regression function model. In practice, when we correct data for empirical analysis, there is no guarantee that there will be no correlations among the regressors or explanatory variables. What we require is that there is no exact linear relationship between two or more variables. Number two, we are talking only about perfect linear relationship between two or more variables. Multicollinearity does not rule out nonlinear relationships between the variables. So multicollinearity is only concerned with linear relationship. So we have to find out or to prove that there is no linear relationship. But while there may be no linear relationship, it's possible that there may be non-linear relationship existing between the variables. That is not the concern of multicollinearity. suppose x3i is equal to x squared 2i. This does not violate the assumption of no perfect collinearity, as the relationship between the variables here is not linear, but nonlinear. Now, how do we interpret the multiple regression equation? Given the assumptions of the classical regression model, it follows that, or we can say that, on taking the conditional expectation of y on both sides of the equation, we obtain conditional expectation of y given the values of x2i and x3i is equal to beta 1 plus beta 2 x2i plus beta 3 x3i. In words, equation 4.2.1 gives the conditional mean of or expected value of y conditional upon the given fixed values of x and 2. In other words, we're determining the values of y on the basis of the fixed values or given values of x2 and x3. Therefore, as in the two variable model case, multiple regression analysis is regression analysis conditional upon the fixed values of the regressors. And what we get or obtain from the average is the average or mean value of y, or the mean response of y for the given values of the regressors. So in multiple regression analysis, what we also seek to get or obtain is the mean average value of y based on the given values of the explanatory variables x2 and x3 and other explanatory variables that may be included in the model. The regression coefficients B2 and B3 are known as partial regression or partial slope coefficients. And that means B2 measures the change in the mean value of y per unit change in x2, holding the value of x3 constant. So in other words, they are referred to as partial regression coefficients because the coefficients are interpolated one at a time, holding the other one constant. That's why we're saying B2 measures the change in the mean value of y, expected value of y, per unit change in x2, holding the value of x2 constant. Or it gives the direct or the net effect of a unit change in x2 on the mean value of y, net of any effect that x3 may have on the mean of y. Likewise, B3, beta 3, measures the change in the mean value of y per unit change in x3, holding the value of x2 constant. So we are taking partial, not all of them at the same time. We are interpolating part by part. One part holding the other part constant. That's why they're referred to as partial regression coefficients, because we can only interpolate one holding the other constant. How do we go about holding the influence of the regressors constant? This is done through the OLS, ordinary least squares procedure, which will be discussed next. OLS estimation of the partial regression function. To find the OLS estimators, let us first write the sample regression function corresponding to the population regression function, i.e. equation 4.2.1 we saw earlier. So we have yi is equal to beta hat 1 plus beta hat 2 x2i plus beta hat 3 x3i plus the estimated error term u hat I, where u hat I is the residual term, the sample counterpart for the stochastic disturbance term ui. As noted earlier, the OLS procedure consists of choosing the value of the unknown parameters so that the residual sum of squares are as small as possible. Thank you for your attention.